to our annual show and tell of work that has been going on for the last either 6 or 8 weeks, depending whether one is a student or on an agile. And
you're in trouble.
We had this year, this is the 9th workshop at Johns Hopkins, and there were 2 more workshops before at Rutgers. Anyway, this year we had 3 teams working. We originally had 4 teams, but 1 team was from China, and they couldn't meet in the spring, and so we postponed them for a year. The reason they couldn't meet is because of SARS, or because of fear of SARS, I should say. So we have 3 teams. The first one that's going to talk today is syntax for statistical machine translation. The next team in the afternoon at 2 o'clock will be confidence for machine translation. I think that's not their title, but whatever. That's what it is, confidence measures for machine translation. And finally, tomorrow will be semantic tagging for sparse data. And the teams nominally consist of 4 professionals and 4 students, but this year we let things slide because one team was missing, and so the teams are enormous, much bigger than this. I mean, it's hard to even count. And so you will see a variety of presentations. I should say that at the end of, toward the end of every section, namely of the presentation of one group, there will be presentations by students who would like to get funding for a year of continuing research on what they started here. And this will be well designated, etc. And we have a panel of 4 distinguished judges here that are going to judge these proposals and rank them, and then if we like it, we'll give them money. NSF has provided us with funds for such a continuation. So I think that's it. Thank you very much, and welcome. And here is Franz Koch, the leader of the translation.
Yeah, good morning everybody. So I will talk about the work that we have done in the last 6 weeks for syntax for statistical machine translation. So first to our team. So we have a quite large team, 12 regular team members, which are listed all here, and 1 additional joker person from the University of Michigan who helped us a lot during the time because they were very interested in that topic. And most of those people will talk, so I won't introduce all of them. So statistical machine translation. In the recent, let's say, 2 or 3 years, there has been enormous progress in statistical machine translation, or in machine translation in general, and due to statistical approaches. So one of these projects, for example, where then this has been shown very nicely, it was in the Working project in Germany, for German to English translation, speech to speech, which are a very small domain, but then more recently in the TIDES project for Chinese to English translation, Arabic to English, or very recently then Hindi to English translation. Enormous progress has been made. If you look at the curves, how performance improves over time, it's really dramatic. And the advantages of using such a statistical approach are well, clear. It has been shown that the quality really improves by doing this. There is a very fast, rapid development cycle for a new machine translation system. For Hindi, it was in a month was built a reasonable Hindi to English machine translation system from starting from nothing. And it's therefore also very cheap to develop those systems. So now I will go over the basic concepts of statistical machine translation. We'll talk about the specific statistical machine translation we are going to use. And so there are already 3 components of such a system. We have to model somehow the problem, the translation problem here then. We have to do training and later on search. So the first problem is a modeling problem. So we have to model a probability distribution of foreign language. In our case, it will be Chinese predicting the English translation of it. And that has to describe the relevant dependencies that hold between Chinese and English. And here we do that specific modeling by using a log linear model that combines a lot of different feature functions, which depend on the Chinese string, the English string, and the word alignment. So we have here all the different feature functions which are combined in a log linear way. We have for each feature function a model parameter, and these are weighted according to that. And these model parameters now need to be trained. So we have now a bunch of free model parameters, and there are various training techniques out there. So often it's used maximum likelihood training, but what in the baseline system we also here in the workshop did is actually maximum blue training. So we directly optimize model parameters with respect to the final evaluation criterion that we use, namely the blue metric, which I will later on describe in more detail. But it's directly basically optimizing on translation quality. And so the specific algorithm used, I won't go into the details there, it's basically a greedy-descent algorithm, it's optimal line search. The advantage of that approach is that it directly takes into account what we want. We want a good blue score, assuming that the blue score correlates well with what humans really like about machine translation. There's a certain problem in this approach, and later on talk more about this. There's a danger of overfitting the training data, especially if you have a large number of parameters. So we have now our model, we have the model parameters, and now we want to translate new text. So in the translation process for new text, our goal should be to minimize the expected loss to make optimal decisions. So we want to minimize the expected loss. The standard approach is a 0-1 loss function, so these are technical details. We will actually later on go more into that by using minimum-based risk approach with different loss function, by directly plugging into the decision rule, then a loss function which is derived from blue, which directly optimizes then the blue score in the search. So before we optimize that as part of the training criterion, but also then as part of the search process. But if we do the standard 0-1 loss function, then in search we just simply have to try out all the different English sentences and maximize this quantity, the sum over all feature function lambdas together with the corresponding feature function value over all possible English sentences. Okay, so these are the basic concepts, modeling, training, search. Now the specific model that we use is a phrase-based statistical machine translation model. And so I won't go into the details, just a picture to describe the basic idea. So if you have a Chinese sentence that is to be translated into an English sentence, what's done is that there is a segmentation performed of the Chinese sentence into these blocks, these large rectangles which you see here. And these blocks are then translated into English. So these blocks here are then translated into, are associated to certain English words. And there might be reordering of these blocks. So for example, here there is a reordering typically, or especially for Chinese to English, they are very often monotone, but sometimes also with reordering. And within the blocks, we also have the word alignment. And so in the translation process, we form the segmentation, the reordering, and the selection of the corresponding English words. And the basic idea in order to train this is to learn all aligned phrase pairs which occur somewhere in the training data and remember these, and then make tricky use of them in the actual translation process. So that's that basic approach to memorize everything in the training data seems to be right now the best approach to learn statistical machine translation systems. And so the specific way then is that we have this feature function, as I said before, in this log linear model. And there are then a certain set of baseline features. So one of these baseline features is the product of the alignment template probabilities. So each of these blocks is one alignment template, and there's associated probability with these, and we simply multiply for these six different blocks, 6 probabilities for these alignment templates.
What is that probability of? The probability of what given one?
Of the English string given the Chinese string. English given Chinese, and simply estimated by relative frequency. So for the word translation probabilities, we have the same. So the words were shown here as black dots. There is also a corresponding product over probability for the words. There are actually 4 different trireme language models which are used as different feature functions. There is the The number of produced words is a feature function, so if the sentence is long or short. The number of produced alignment templates is a feature function, and some other different feature functions. So altogether there's 12, in the baseline system there are 12 different feature functions which score each of the sentences. Okay, so how good does this work? This system has been evaluated in the recent NIST evaluation for Arabic to English, Chinese to English, Hindi to English. So we work here in the workshop for Chinese to English. So one thing, so here we see the results of the alignment template system on the NIST score. The NIST score is basically a score, I won't go into the details, but larger numbers are better. And we see here the competing system, or this commercial off-the-shelf systems. And we see that the system achieves quite good performance. Increase over time, it got really dramatically better. And compared to what commercial off-the-shelf systems what you can buy on that task, it seems to be quite good. And similar results, so that's this automatic score, and also the humans, at least in 2003, agree with these evaluations. But so, if we actually look into the output of that, it doesn't seem to be too good. So there are still a lot of problems in these outputs. And especially, it seems that the statistical machine translation often makes very stupid errors. We really say, so why does this happen? That it must be straightforward that can't be right. So for example, there are often missing content words. MT output is condensed US interference in its internal affairs, and the actual correct translation would be that the Ukrainian did this. And that's very important information in that sentence. Without that information, there is really something crucial missing. And it should be straightforward to say, okay, such a word should not be omitted in the translation. Or there are verb phrase problems. Indonesia Z oppose. It's not really grammatical, so it should be possible to see that, for example, this Indonesia reiterated opposition is a better verb phrase for that sentence. There are wrong dependencies. So for example here, it's not understandable. Sometimes these wrong dependencies lead to really misunderstandings, but here, particularly those who cheat the audience, the players, but the correct thing would be particularly those players who cheat the audience, so the dependency has been flipped and not transferred correctly. Other problems are missing articles, that then this word here has no article. And these are actually very nice sentences where then there is a specific problem in each of these sentences. So very often the output looks more like word salad, where then the word arena on top of the US sampler competitors and since mutualite. And so you actually, if you read it a long time and try to figure it out, you can make some sense out of it. You can get a feeling for what's going on, but it's more word salad. So we don't like these translations. We would like to have something better. And so machine translation made a lot of progress, but it still produces a bad output and especially makes stupid mistakes. And many of these problems are somehow, in some very loose sense of the meaning syntactic, are syntactic. And possible reason for that is that this baseline system, state-of-the-art machine translation, phrase-based statistical machine translation, doesn't know enough about what is important to humans. And the idea is to take into account syntactic dependencies explicitly into the model, which are right now only implicitly there by memorizing everything that has been seen in the training data, but to add these explicitly into the model.
Excuse me. I'm just wondering, are all these comments generic comments, or are they specifically aimed at Chinese to English translation problems, which will have certain unique problems associated with it?
They are more or less generic. So for example, for Arabic, the machine translation quality seems to be better than for Chinese. But still, if you look at the output, there are basically the same problems, that asyntactic sentences. On average, you get nicer sentences. But there is still a huge gap between what the machine does and what humans do, even bad human translators. So there's a huge gap there. And the problems are more or less the same. So the specific plan now is that we start with the best state-of-the-art statistical phrase-based statistical machine translation system. So we use that alignment template system exactly on this task, where also the NIST machine translation evaluation have been, as I've shown. And that system is purely data-driven. And then we tried to make an error analysis. What goes wrong? What are the problems? How can we fix them? And the idea is to develop syntactically motivated feature functions for specific problems. So directly look at that system, what goes wrong there, and then develop feature functions that try to avoid this error. So if the verb is missing often in the output sentences, then we develop a feature function that tries to make sure that there is a verb. So, and these feature functions depend on, well, the standard things, where the baseline feature functions depend on the English string, the Chinese string, the word alignment, and the phrase alignment. So that's where the baseline feature functions already have a dependency on. But in addition, they can depend on, for example, the part-of-speech test sequence of the English and the Chinese string. A chunk segmentation for Chinese and English. Right now there's segmentation into phrases, but these are not linguistically motivated. These are just what has been seen in the training data. Path trees for Chinese English, or dependency passes for Chinese English. So all these might be possible dependencies for these refined feature functions in order to make a better decision. And so the major tasks are then, as I said, error analysis, feature hunting, special approach which we did was contrastive, or what we call contrastive error analysis, and we'll talk later on about that. Developing then new feature functions, introduce these new feature functions in the training procedure, and do then this maximum blue training, or we also have investigated perceptron approach to training, and try then our different search approaches, namely also this minimum-based risk approach with specific syntactic loss functions.
Just another point of clarification. I guess the assumption here is that in the set of feature functions you're currently using, you don't have a lot of feature functions aimed at syntactical issues.
At least not explicitly. So implicitly there's, if you have a large phrase, which has been seen in the training data, and the translator actually produced that large phrase, that somehow captures a lot of the syntax. But it's not explicitly there. And our idea is that these problems, we have the feeling that if we explicitly tell it, don't avoid articles, or don't avoid verb, if there's a verb phrase in the Chinese, then there should be one on the English side. If you tell this explicitly, then translation should get even better. Because the baseline system has only this implicit concept there and makes often mistakes because of that.
Will these feature functions be specific to the input language or the target language or both or neither?
So some of them will be specific only to the target, only looking at the English side. But many of them also then take into account the Chinese and the English. And yeah.
So in response to Michael's question, you said phrases a couple of times, but you should perhaps emphasize that to the baseline system of phrases, the number of words that appear next to each other. This is not any linguistic notion of phrase. So there is, in that sense, there is.
So, and specifically, we want to work on the Chinese-English large data track of the recent TIDES machine translation evaluations. And so here I will talk about the specific data that is going to be used. So the training data for these baseline feature functions are actually quite large, 150 million running words per language, so Chinese and English. The reason why we chose also Chinese was because there's a Chinese tree bank available to train a Chinese parser. And then we use what we call development data for this maximum blue training. So there has been in the NIST evaluation 2001 set defined with 993 sentences. And on that set, we tune the model parameters for this log linear model that is used in order to combine these feature functions. And then we have a test data set, which is NIST evaluation 2002, with 878 sentences. And on that, we then evaluate if our feature functions really improve. And we also have blind test data held out, which then will be used for after workshop evaluation of the system, which has 929 different sentences. And we prepared also a larger set of development test data, which we made some experiments on, but most of the results we will present are then on this setting of development and test data. And a statistical machine translation system is a very complicated large system, so a lot of components are in there, and the training procedure to get them from the parallel text, which is there in the beginning, to a final system is very complicated. And during the workshop, it would have been a lot of trouble to work with a full system. So what we do in the workshop is to rescore only in best lists. So the approach there is that our baseline system is trained on this large amount of data, and then produces for this development and test data for each of the sentences alternative translations. And later on in the search process and training process, we only take into account these alternatives that have been produced there. And that has a lot of advantages, so there is no need to integrate the new feature functions that we develop into dynamic programming search, which would be very, because for each of these feature functions we have to think a lot about how to make an efficient search there. The feature functions can also depend arbitrarily on the full Chinese and English sentence or pass through everything. So we don't have to constrain our dependencies to say we only want to go from left to right or that, or we only want to, because our search architecture is from left to right. But we can arbitrarily depend on anything in these trees. And on all these different levels, part of speech level, the original word alignment, the Chinese English string. That allows in a very simple software architecture and for rescoring, we just go over all the sentences and compute the score and put the highest scoring sentence to the top. And using then a fixed set of invest alternatives, effectively a feature function at the very end after we have computed it, is basically a vector of numbers. And that's then used, this vector of numbers is then used afterwards in the machine learning approach in order to make optimal combination. So that very nicely separates out the machine learning from the modeling. And there is a certain disadvantage that the limits are improved, the improvements are limited to the current investors. So we cannot go beyond that, or only in a very limited extent. We actually did a little bit go beyond that, but only to a limited extent can go beyond what's in there in the investors. So the improvements you can obtain during the workshop are also limited to what's there. I will later on talk about what are these limits. And so what we did before the workshop to compute 16,384 alternative translations for each of the development and test sentences.
Is that total for all the sentences or for each sentence?
For each sentence. So it's a huge set of over 220 million.
16,000 decimals.
Yeah.
But the training corpus itself, the full 150 million words, is not being used here?
Is also used. For some of the feature functions, we also use a very large corpus. But for example, for all those feature functions we take into account the parsing, we took a subset of that corpus because the parser needs to be applied to each of these sentences. So we used a smaller set for the parser, not say 150 million, but 30 million words. We will later on talk more about the data that has been used and for the syntactic tools. So how are we going to evaluate the system, or which results will we present? So the evaluation metric that we use is BLEU. The basic idea of BLEU is that we compute the precision of the n-gram produced in the translation, 1, 2, 3, and 4 grams in our case here, and form the geometric mean of this precision. So if the precision is high, then we assume it's a good translation. If the precision is low, we assume it's a bad translation. And in addition, there's a refinement, a penalty factor for 2 short translations in order to avoid that people can gain the metric by producing only a single word translation, for example. And it has been shown that this BLEU metric correlates with what humans really think is a good translation. But very recently then, especially, or one possible reason for that is because MT got so much better in the last time, so that the MT performance looks too good compared to human performance if we measure that with BLEU. And so there's a certain problem there. And the important question for us in the workshop is BLEU good enough in order to measure subtle, at least for BLEU at least, subtle syntactic improvements, changes in the system? And we'll also talk more about that during the talks later on. And as after workshop, we plan to make, in addition to that, in order to be sure that we really improve the system, a subjective evaluation of the final system by really asking humans if they like the new translation better than the old one. And so what are the possible improvements that we can actually get if we fix ourselves, constrain ourselves to this invest list? And so in order to define that, so we talk about Oracle BLEU at some points in our talks. So the Oracle best translations, according to the metric, is that set of translations that gives the best BLEU score on the test data. So if you have Oracle, which says us from at least 1,000 best feedback, that sentence and that sentence and that sentence, then this set of sentences that gives the best BLEU score is a so-called Oracle best translation. And then correspondingly we can define the Oracle burst translation of those which are the burst scoring translations according to the invest list. And obviously if we constrain ourselves to that invest list, we cannot get better than the Oracle burst. So there's a hard limit there. And to actually compute that for Bleu is non-trivial. I don't want to go into the details, but we use a greedy search algorithm in order to search for this Oracle best and worst translation. And what comes out? So this comes out. Here on the axis we have the n size for the invest list. So the first best has a Bleu score of 31.6. And then we have 2, 4, 16, and so on, up to 16,384. And we see that there's a nice improvement. It looks almost linear on this log scale. That the Oracle best gets a Blue score of up to almost 50, so I think it's 48.5%. And the Oracle worst is here. So in the end, if you have a very good, extremely good training technique, we could reach that point here. And if we have a very bad, the worst training technique, which could, in the worst case, come here, we could never get worse than 16% Blue score. So, so how good is, it's quite interesting to see how good is the Oracle then compared to humans measured by Bleu. So to do that, we computed the average Bleu score for humans. On the average Bleu score, we have this, in each of the sentences, we have 4 reference translations. And so the average human score is then, if you take out one reference and compare it to the 3 other ones. So we obtain 37.9% if we compare each of the humans to the others on average. So that is important.
Some doubt on how well Bleu models human intuition. I assume that if you gave human translations to other people, they would prefer them over your programs.
I will talk about that.
So what is that famous line? You could possibly think so, but no, but you may possibly think so, but I couldn't come.
But I will talk about that.
I couldn't disagree with you, man.
So if you take the first best, so what the baseline system really produces as first best translation, and use then this 3 references do the same thing for the humans, you get an average Bleu score, average first best score of 27.6%. And so relative to human, so that's these numbers which I recently always mentioned, we have a score of 72.9% if you do that.
I'm sorry, I'm saying that again. What is the difference?
So here we have this average human score by always taking out, we have 4 references, by always taking out one of the references and scoring it to the other 3. We get 4 numbers and average this.
Right.
And in order to get a comparable number for the machine, we do the same here. We average the corresponding scores which the machine obtains using always this subset of 3 references.
So you pull out, just to say it again, the human case, you pull out one translation, compare it against the other 3s, apart from getting yet another human to come in and do a translation, right?
We only have these 4 reference translations, so we have to work on these. And that's the reason actually why this procedure is done. That's a standard procedure that how normally these relative to human Bleu scores are computed.
So I think the thing that's confusing here is we're just multiplying the Bleu by 100. So that 37.9, that's a Bleu score. It's not a percent of something else.
Yes, no, I understand that. But I'm not, yeah, what does this mean? Well, maybe
that's a different question. What does this mean? It's a useful thing to do. It's often done. So and it's quite interesting to look now at the numbers which will appear right now here, or in a few seconds here, if I continue. So that's the only. It's a standard thing that has been done. Interesting to look at these numbers. I don't want to give too much interpretation to this, and I don't think that so there has been a lot of discussion at the last TIDES meeting. If that really means that the machine is at 70% of human level, and it doesn't mean that. But measured by Bleu, it's this number. Measured by Bleu, we are at 72.9% of human.
And n equals 4. So n equals 4.
N equals 3.
Yeah, 3.
No, n-gram size.
N-gram size 4. Right.
Because less that n equals 6 and 8 and so on.
I will also talk about that in a minute.
Is it Oracle or is it the copy and
This is the current system.
So I mean this 27.6, is it the Oracle or is it just...
No, that's the average first best score. So not the Oracle, but the first best translation of the system, of the baseline system. So yeah. So that's on the previous slide, the one which has then this 31. So if you use the first best, it has 31.6, but that is 4 references. So now, in order to compute that number, we work with 3 references, and then it's 27.6. It's a smaller number. If the number of references gets smaller, then the number gets smaller.
But the previous size was the oracle, but this one is not.
No, that's this number here is the first best of the system. And this is then, if you only have one best, the oracle and the first, it's identical. If you increase the n best size, then the oracle gets better. The first best obviously remains always here 31.6, that doesn't change. But that's then the oracle later on.
And people are at 37, right?
Yeah.
Right. Well, they are actually a bit higher because of the. But let me continue. We shouldn't go into machine translation evaluation discussions because these typically don't end.
The problem for me here is to understand if that score going up means better translation. And that for me is completely unclear. I mean, that's not
Right. I completely agree.
It's baloney.
That's a big question. If that score goes up, if humans like it better.
So
Let me talk. I actually wanted to come to all these points now, but okay. So the average so what comes out, average oracle of the 1,000 best blue score. We always work with 1,000 bests in our system later on. We don't work with the 16,000 bests. And so the blue score of that, in the same comparable blue score, is 39.8%. So the relative to human blue score is 105%. So looking at that, we have very good possibilities in order to we just need better learning and then find the best sentences, and we are much better than.
But another point you're making is throughout the rest of the talk, the team only looked at the top 1,000, not the top 16,000.
Right. And already for the top 1,000, we are at the 105%. So the top 16,000, we are over 100%.
You get to 50%, is what the previous curve suggested, right?
Well, that's this score is relative to humans. The point is that because humans are then at this other
No, just
score.
commenting that here, with the 1,000, you get up to 40. The previous curve, the graph you showed, suggested that at 16,000, you get up to 50, that's all.
Right. But also the number of references change, so the numbers are not directly comparable, but more or less, yeah.
Maybe it's worth pointing out that if you raised 1,000 to infinity, or sufficiently large, then you could get 100% blue score because eventually you get more reference translations.
Right. Exactly. Right. But the quality of the oracle is still very, very bad. And we all actually looked at the quality for very many of the sentences, everybody in the team, and looked at the reference translations. And the oracle is, in almost all the cases, much worse than the references. And so these numbers have to be taken very carefully. And that basically also shows limitations to GLUE, at least as soon as the systems go into this relative to human blue score level of 7%, or in Arabic we are even higher at 80%. And then, we have to keep in mind that these numbers are only with respect to GLUE and not talk about real translation quality. And so at one point in time, I think that shows we will need a better evaluation metric in order to really measure progress in machine translation. But I think almost everybody in the machine translation community agrees that there will be some time that will be the best metric. Right now it's the best metric out there, we don't have anything else. But at some point in time we need a better metric. And okay, so we have now these oracle translations which are better than the produced translations, but are not better than humans. And the oracle translations still contain a lot of errors, but they are hopefully better. And then we do what we call contrastive error analysis. So we compare the produced translation, or the first best translation, with a blue score of 31.6%, with the oracle translation with a blue score of 45% or so. And then basically you can do this quantitative by simply looking how often certain properties hold in the oracle and how often certain properties hold in the produced translation. And depending on these differences we see, probably we can do something about this, because there's a systematic difference between produced and oracle, and we would like to produce the oracle instead of the produced. And also qualitative, what we do is we actually look at these sentences, we look at the produce, we look at the origin, we look at the references, and as humans we look there and decide what kind of problems are there, how can we fix these problems, and what kind of feature function would help us to prefer instead of the produce the origin translation. So that's, we as humans expect that and try to define what can be done. And the basic approach then this is what are the next low-hanging fruits. So we look at a lot of these translations and find that is the major problem there, so we develop a feature function for that major problem and hope the system gets better, fixes that problem, and then we continue and iterate over that to always pick the next low-hanging fruit. So so then some highlights about the following talks which are going to be done. So actually we did improve on the best known Chinese English machine translation results so far, so we later on see a lot of numbers to show that. We developed 450 different syntactic and other new feature functions on various levels of syntactic analysis. So low level, or what we call implicit syntax, shallow level, deep level, or what we call tricky syntactic feature functions. And so we had to parse a lot of sentences. We actually parsed 7,965,393 different sentences for the English alternative translations. We actually parsed these a few times because our disk crashed once, and so we had to reparse it. But in the very end, we had this number of passes on our list. And we used various different parsers, but mainly Collins parser for English and then Wikis parser for Chinese. And so for these alternative translations, in best list, we used a 16,000 best list. Altogether, we had 290 million alternative translations, and we filled up our disk after 1 week. So now to the following talk. So I give a presentation outline. So I talk now about the approach and motivation. Then Dan will talk about syntactic framework and preprocessing. So what kind of parsers we use in more detail and what kind of basic syntactic framework we use. Then we talk about the different feature functions. So David will talk about the implicit syntax feature function at a low level, things which doesn't take into account parse trees or part of speech text or so. Then we will talk about Alex and Zen will talk about shallow syntax. Then we will talk about deep syntax, Kenshi and Catherine. And then what we call tricky syntax, which does tricky stuff. Anoop and Varen will talk about that. Then we will talk about rescoring techniques. Instead of this maximum blue training, we also investigated perceptron learning. Libin will talk about that, and also minimum-based risk search, Shankar. And then we'll talk about the feature combination and evaluation in the end. If we have all these features, how did we combine them and what results we could obtain end-to-end. Then there will be the 2 student proposals, and I will conclude. Okay, that was the first point.
I have a question. You said you had 450 syntactic features.
Right.
How many? And at the beginning of the talk, you said you started with 12 features. So this is really dominating your log linear scoring function.
Right. If we actually use all of them at the same time, then it will dominate it. Later on, we will show how we did then the combination of the different feature functions. And normally we edit always one feature in order to see if that feature is informative or not. And in the end, we also try to make different combinations of these. And we actually didn't use all the 450 features at once, but sampled the good ones out of these. So the 450 features are those which we have developed. Not all of them are really improving the system.
So if you were to field a system now, how many additional features would it have?
Well, I think the feature combination system in the end had 25 features or 30 features, between 25 and 30 typically.
Okay, so I'll be talking about some of the pre-processing of the data and the sort of general syntactic information that we used for all of the features in the workshop. So the basic processing that we applied to all of the data was part of speech tagging, chunking and parsing for both Chinese and English, and I'll go through some of the issues for that. Also segmentation for Chinese. Some of the particular things that we had to deal with for the MT system were issues dealing with case and different tokenization standards. And I'll just talk a little bit about what happens when you try tagging and parsing the output of the MT system, which doesn't look quite like the English that these tools are normally used to seeing. So I want to acknowledge the various tools that we've used. So Chinese word segmentation, we use both the system from LDC and one from Penn. Part of speech taggers for both Chinese and English. The parsers on English we used both Collins and Charniak parsers. The Chinese parsing was done mainly with Dan McBell's parser, and we also used the chunking system from Johns Hopkins. Here's an example of what the output of a parser looks like. So this is a entry bank style parse tree, and this is also the format that our, for example, Collins parser will give. So this tells you things like this is a sentence with a noun phrase and a verb phrase. You can read things like what the subject and the object of the verb are from this. And the lowest level here is above the words is the part of speech tag. So this tells you that this is, for example, a singular verb, or singular noun, plural noun, past tense verb. And we have the same sort of thing for Chinese. So this is what a Chinese tree bank parse tree looks like. So this is the format. There's a few differences. So for example, we have IP instead of S. That's basically just a different name, but there's a few other things. For example, there tends to be more structure in some of the noun phrases. So for example, here in the same sentence, there's a recursive noun phrase under the main noun phrase, whereas the English structure was flatter. There also tends to be more levels for things like quantifier phrases and adjective phrases. And of course, the part of speech tags at the bottom are different because of the differences between Chinese and English. So for example, we just have noun here instead of singular and plural noun. So it's not marked. We also just have verb instead of present or past tense verb. And then there's a few new things like M stands for measure word here. So that's a full parse tree. We also used a chunk representation, which is sort of like the lowest level of the part of speech tags, sort of the base non-recursive phrases in the parse tree. And this just shows what that looks like for the same sentence. So we have a noun phrase, and the verb phrase here is just the verb. And similarly in Chinese, here the noun phrase is broken up. Again, because there's generally more structure indicated in the tree bank trees for Chinese. So we ran all of these tools on as much data as we could. So both the training data that was used in training the original machine translation system and the NBEST list that we were rescoring. So we took a subset of 1 million sentences, part of speech tag, chunked and parsed them, both on Chinese and English. And we also used the FBIS data, which we sort of focused on for some of the parsing tasks because it's generally cleaner data. And again, for the NBEST list here, we had just one Chinese sentence to process, but 1,000 English versions from the candidate translations, all of which were tag, chunked, and parsed. One issue that we had to deal with was that the MT system just produces lowercase output, and the taggers and parsers that we're working with expect regular mixed case input. So we actually wrote a tool to go from lowercase to try to guess whether something should be lowercase capped or full capped. And this was done using basic language, n-gram language modeling approach to try to predict the most likely case sequence for a set of uncased words. And it has a 3.3% error rate, which was seemed to be better than some other systems that we looked at. We also had to deal with the difference between tokenization standards. So there are a few differences in the tokenization used by the baseline MT system and the tokenization that the part-of-speech taggers and parsers are used to. So as one example, here with hyphenated words in the MT system, the hyphen was broken out and there would be 3 separate tokens here, whereas for the parser this is just one word. Also and or, for example, is handled differently. So we wrote a tokenizer to go from the MT output to the format used by the parser before running the parser. Now, for a lot of the feature functions that we're going to be talking about, we wanted to use the word level alignment between the Chinese and the English candidate translation. So the MT system produces that. So in our NBEST list, we have the alignments used by the system during decoding. However, the tokenization in those in the NBEST list didn't match the tokenization in the parse trees. So we wrote a new tool to align the 2 tokenizations, so the English to English. And this was done just using a string edit distance dynamic programming algorithm where things could be replaced, they could be split from 1 token to 2 tokens, and it knew that ones with that were substrings of each other were likely substitutions, and deletions were not possible in this case. So that gave us an alignment from one English tokenization to another that was composed with the original alignment from the MT system to let us line up the Chinese words with the English words in the parse trees. Another issue was that not all of the words in the NBEST list had all of the alignment information because of a separate rule-based sort of post-processor that is used to translate things like names and dates, numbers. And so we sort of found the alignments just for those cases with like training a new word alignment tool and a statistical tool based on the IBM models, and just applying it to these rule-based translations and then splicing in those alignments with the alignments from the statistical MT system. So we ran into some issues with processing the output of the MT system, which is not, often not grammatical and generally doesn't look like the data that the taggers and parsers were trained on. So this is just one example. Here we have a sentence candidate translation that doesn't have a verb, but part-of-speech tagger really wants to find one. So it decides that achievements in this particular context is most likely to be a verb, even though it's never seen achievements as a verb in the training data. This was an issue because the candidates are ungrammatical, but also because our MT data includes a lot of headlines, which often are not complete sentences, don't have a verb, whereas the tagger was trained on pen-treatment, which generally doesn't include headlines.
Excuse me, I hate to slow things down, but I'm losing the point here. You have an English parser, you have a Chinese parser, you have an empty translation system that can take Chinese and turn it into English. What is the issue with the fact that the outputs of the MT system don't exactly align with the English parser of the sentence and the
Well,
Chinese?
we're going to want, as we talk more about the specific feature functions, a lot of them are going to depend on the fact that this particular word in English corresponds to a particular word in Chinese. And so we're going to want to, for example, compare the parse tree structures around those two particular words, but we want to know which corresponds with which.
You're also going to want to dig sentences with no verb, right? So if the tiger thinks there's a verb, then you can't dig it.
Exactly, yeah. Okay, so this was also an issue with punctuation. So if you thought it was weird to have achievements as a verb, how about achievements as a punctuation symbol? So again, here the tagger's trained on sort of normal-looking sentences that always have punctuation at the end, which isn't always the case in the NT output, and also isn't always the case with headlines. So those are some examples with the part-of-speech tagger, but this also applies to the parser. So if the parser, well, if the tagger says that achievements is a verb, the parser will believe it. But even if it doesn't, so for example here, the parser can end up doing some strange things. So the parser also wants to find a verb or a verb phrase, and it's used to seeing sentences that have a noun phrase and a verb phrase. And here it ends up finding a verb phrase even though there's no verb anywhere down here. Okay, so what that means is that features like, is there a verb in the sentence according to the tagger, may not do what you think, or is there a verb phrase in the sentence, may not do what you think. And so that's just sort of something to keep in mind as we go through the feature functions in the rest of the talk. And things that we looked at for this are, for example, using the probabilities of the parsing model to tell you, is this a good verb phrase, or looking at more of the structure, so is this a verb phrase that actually has a verb, for example.
Should one try actually to fix the parser to accept fragments without verbs, so that you don't have to do later rules?
Yeah, probably, but we decided we couldn't really do that. Let's go to the workshop.
Aren't there some languages that never have R or is?
Oh, well, sure. I mean, a parser trained on those languages would do well with grammatical sentences in those languages, for example. But there's still issues with dealing with noisy here. So we didn't have to deal with the noisy data for Chinese. So the Chinese sentences that we start with are grammatical, but there are some other issues. So in particular, we have to segment the characters into words before doing any of this processing. And it turns out that the parsing is very dependent on the segmentation. Now, for example, this was a problem a lot with proper names, and you'd see somebody's name translated as some weird thing like from the sea life, and if you trace back through the system, that would turn out to be ultimately due to the segmentation. Even when the segmentation is perfect, the Chinese parsers aren't as good as the English parsers. So on ethnic label constituents, it's about 82 versus 90% for English, partly because there's less training data available for Chinese, but also because there's, for example, less inflectional morphology in Chinese that distinguish nouns from verbs or to give you pretty more information. And for some reason that we're not entirely sure about, Chinese parsing is also a lot slower. The parsers don't always return a parse. So in our best list, we had no parse for about 3% of the English candidates and 4% of the original Chinese sentences. And that's just something that we sort of had to pass through the pipeline of the feature functions that deal with parse trees will have to
Is it really
handle
true
some.
that my parser would refuse to return a
This is Hopkins.
Can I answer this question? The Chinese parse actually does a better job because it handles up to 300 words, and Colin stops at 119 words. So you have a discrepancy from that. Yeah, and then the other difference is that the Chinese parse usually tries to find as much less frequently than the Collins parse.
I mean, if you can send me a sentence that my parser refuses to parse,
Okay.
I'd like to have it. Under 300 words.
Under 300 words, okay. Well, this is the problem. So. Okay, so that's it for the pre-processing, and so now we're going to go through the features. We organized them into these 4 general categories, which aren't always very sharp, but we tried to organize it from sort of low level to high level. So starting with what we call implicit syntax, which is things that are purely data-driven at the word level that don't use the sort of syntactic annotation that I've just been talking about. Shallow syntax refers to things that use part of speech and shunt information. Deep syntax is things that look at the entire parse tree. What we're calling tricky syntax is things that use the entire parse tree but decompose it in various ways to make it more manageable for calculating the feature functions. And this, again, is just one way to organize it. So other things to keep in mind are features that just look at the English versus the correspondence between the English and the Chinese, and things that use the word level alignment between the two versus things that don't. And like I said, then I guess I'll turn it over.
So naturally, since this is a workshop on syntax for statistical machine translation, we'll begin with feature functions that have almost nothing to do with syntax. You can justify this in some ways. The highest cannot stand without the lowest. You can also justify it in a practical way, in that we don't want to get caught out trying abstruse and glorious syntactic whole tree feature functions without having tried the stupid things that were left out of the baseline system. Such things as different kinds of language modeling that weren't part of the original 12 baseline feature functions, different new consensus and hypothesis augmentation techniques such as multi-sequence alignment, stronger evidence for the conjunction and reordering of these alignment template phrases which make up the baseline system. And also simply larger whole sentence models for word translation that couldn't have been taken into account by the left to right search and decoding. So obviously there are a lot of feature functions, as Franz tried to give you a taste of. So what I'm going to touch on are simply some of the highlights, whether in results or perhaps technical interest. And anything left out here will be rounded up by Sanjeev in a series of monster tables, which you can all look forward to at the end. For example, in language modeling, various skip language models can perhaps be justified for this dirty, empty output, the disfluent output, where you can interpolate between the immediate preceding context and one-word prior context. Very simple feature functions that try and account for omitted function words such as that, the words that in English that have no correspondence in Chinese, and thus we can presume that just simply upweight translations that display more of the connective tissue of English will do better. Features such as a word's popularity, the invariance in multiple translations. So you look at multiple translations and see where the translators all agree that a particular kind of word or class of word has to be there. And then you give that a higher weight than the sorts of words on which translators tend not to agree. As well as, for example, a very specific and low-level model, the probability of a word triggering its repetition. This is the kind of error that an alignment template system seems to make in that neighboring Chinese words trigger the same kinds of content words, and thus you intend to get investment, scale investment. It's a very pleonastic statement. whereas what you would like to pick is out of the unbest list a large-scale investment. Some other techniques that have, for example, shown some promise in speech recognition, simply finding consensus among various hypotheses in the n-best list. So you can produce a multi-sequence alignment on this n-best list by finding the sentence pairs with the smallest edit distance between them and agglomeratively clustering up until you get something like a generalized lattice like this. And in the simplest version, the arcs on the lattice are simply weighted by the number of hypotheses that agree that this token appears at a particular point. And then this lattice can either be used to generate new hypotheses, or within the feature function framework can generate some feature functions such as the weight of a hypothesis as it traces its path through the lattice, or a binary feature as to whether a particular hypothesis agrees with the majority arcs in a lattice, or how many majority arcs it agrees with. And although we didn't do very extensive experiments at all with augmenting the n-best list, since certain baseline features such as alignment template cannot be recalculated with great ease on these. Jen will also talk about some of these experiments in another domain, and in future I expect this will be done more. As to some other very low-level features specific to this system, alignment template ordering is an issue that that isn't explicitly addressed in the baseline system. So while the words within an alignment template have been seen many times in training data, and we can model their reordering, the evidence is less strong for where we should segment the input text into alignment templates and how the reordering should be done. Obviously, there's some modeling that goes on, but here we can look at some whole sentence metrics that weren't available to us before. So we can, for example, look at the probability of joins that preserve a monotone ordering, as one often sees between English and Chinese, and ones that don't preserve such an ordering, as well as looking at the particular strength, the support for a particular juncture between alignment templates. This is probably best illustrated with a figure where, for example, the second alignment template here is left monotone with its neighbor to the left, the 2 points join. And so you can calculate the probability at each join that it will be left monotone, whereas this one isn't left monotone, so you have a probability that it isn't left monotone, and you can produce a probability score for that sentence. Likewise, you can look at right continuity, where does the last word in the alignment template come right before the first word in the next alignment template? And so you can produce a right continuous score for a sentence in that way. And Hopkins runs have implemented various variants of these feature functions. And actually, Franz also computed another metric on the alignment template joins, trying to see, there's the one Viterbi alignment template sequence, if you will, and there are many alignment templates that have been memoized from the training data, and one can ask how many of these fixed phrases or phrases with class slots can be found that also overlap with this join, thus showing that this is the kind of word sequence which is favored by the training data and isn't simply a juncture of two unrelated phrases. Then, as Franz showed, there's still weaknesses with content word translation, Ukraine dropping out because of the vagaries of the probability model. So you can specifically model the omission of content words. Look at the words in the Chinese, look at the translation lexicon, and penalize translations if they don't contain the appropriate content words. Or one can also produce a more holistic models, something even as simple as IBM Model 1, which, while not the not the best translation model for producing new translations, can give a score to each of the hypotheses in our n-best list. So it's an additive model. It's not, you don't just get the Viterbi translation. So for each word in the Chinese sentence, sum the probabilities that all the English words in the hypothesis translate as that Chinese word, and then produce the combined probability. Model 1 tends not only to help you in producing content words in the translation, but also capture some of the triggering effects that happen among words. And now I'm going to give the game away and sort of show that we're glad we tried all these non-syntactic features, because they end up doing pretty well. So IBM Model 1 is among the best performing single feature functions that we tried.
Baseline is what here?
Pardon?
The baseline.
The baseline is 31.6.
31.
Right. So this is certainly, and given the size of the test set, we are statistically significant at 32.5 on the smaller test set.
And this is all with the rescoring, so the best you're going to get is, in a perfect world, is like 37 to 38.
Right, right. And this is with only adding this one particular feature to the 12 baseline features. They're always around, and then you just add one of them, and then feature combinations will come later. The ordering of the alignment templates also helps a slightly lesser amount, as well as missing content words and overlapping alignment templates. Simply using some of these language modeling techniques as individual feature functions doesn't help against the baseline when used as single features, although they can help in the feature combinations after the score has been driven up by some better functions.
And again, this is, each one of these is independent of each other. This isn't a cumulative.
In this slide, no. Yes.
And you're going to have a cumulative site, you're going to have the whole mess.
Right. So because we can't just throw all the features in at once, our working procedure was to score all of the features individually and see how much they help, as well as to do some more qualitative evaluation to see.
This is dev set stuff, right?
These are test set results. They're trained on dev and tested against the small test set, not the blind test set.
It's not the blind test set, it's the test set. So there's some potential overtraining.
Right, there is some potential overtraining. Although we didn't look at it, we've done so many experiments that we stand guilty yet.
Has IBM Model 1 already been accounted for in the translation model itself? So can you explain a little bit why here IBM Model 1 actually can be a very useful feature?
Well, I don't, unless I'm misunderstanding, I don't think IBM Model 1 is accounted for in the alignment template framework. As I said, probably the best accounting is that since it's a cumulative model, it doesn't just give you the one best translation when you're calculating these probabilities. It has properties that aren't reflected in the left to right decoding that are done in the baseline. That's done in the baseline system. So, having cleaned house with all of these non-syntactic feature functions, we claw our way back into realm of syntax, and Alex is going to talk about the first.
When is the break?
After 10, actually. That's right, so about 15 minutes from now is the break. Okay, so I'm going to talk about shallow syntactic feature functions, and this is an overview of what I'm going to talk about. First, I'm going to talk about why we work at the shallow syntactic level. Then I'm going to talk about 5 specific interesting shallow syntactic feature functions, talk about the results on those, and then Zen will talk about 3 approaches for improving punctuation. So why would we want to scale up from implicit syntax to shallow syntax? So the basic idea here is we can use external linguistic resources to improve generalization. And the advantages of working in shallow syntax, so that part-of-speech taggers and chunkers are efficient, Decisions are local and they may function better than parsers on noisy MT hypotheses. We have 1.3 million tagged parallel sentences for training if those feature functions require some underlying probability model. And the simple models allow quick reaction to problems evident from the contrastive error analysis. The disadvantages are that the part speech information is implicit in the baseline system in the translation table. The chunks are roughly at the alignment template granularity. They're actually a slightly higher granularity, but consecutive word phrases may capture a lot of the information that's present in the chunks. And of course, the generalization power is less than going up to the full syntax of deep syntax or tricky syntactic methods. So I'll start off with some very simple feature functions, part speech and chunk tag counts. So the motivation here is that the baseline low-level syntactic problems, such as overgeneration of article, comma, singular nouns, and we also have undergeneration of pronouns, past tense, coordination, and plural nouns. So the idea here is that the re-ranker can learn to favor a more balanced distribution of tags. And the implementation examples are that we can implement tag count and tag count differences, such as the difference in number of noun phrases from Chinese to English in the chunk parse. Or we can also look at tag translation counts, which actually use the word alignment. So how many Chinese N tags, any Chinese tag starting with the letter N, so it's a nominal tag, are translated to only non-N tags in the, on the English side. Moving up in complexity, we go to tag fertility models. Here we look at the actual tag distribution, and the idea is to improve the English tag distribution using the Chinese tags. So this is implemented using a bag of tags model. It has some similarities to IBM Model 1, but it actually models tags with zero counts explicitly since there's a small number of tags. And we just look at the conditional probability of the number of English tags given the number of Chinese tags. So for instance, we can look at what is the probability of seeing 2 NPs on the English side if we saw 1 on the Chinese side in the chunk parse. And what is the probability of seeing some coordination on the English side if we didn't see any on the Chinese side? Or even things such as, what is the probability that we see a number on the English side given that we've seen a measure word on the Chinese side? And these are just combined in a log linear fashion using the opt-in best framework. And various combinations were tried. Smoothing is a large issue, as you'll see in the results. And a parameterized distribution on the ratios might be better, probably a good thing to try next.
What do you mean by the ratios?
So the ratio, so for instance, rather than looking at these, at the probability that we have given one Chinese NP, we get 2 English NPs, it might be better to say, okay, I want the ratio of these two to be, I want to model the probability of the ratio of these two given as a Gaussian or something like that. So I think that might be a better way to reduce parameters and get better results. So lexicalized chunk features, another family of feature functions. The motivation here is that the part of speech information is too local, but not all chunks reflect longer dependencies. So the idea is use the NP, VP, and adjective P tags from the chunker and otherwise use words. And this is a very simple implementation. We process the English or the Chinese into a chunk sequence. We build a language model on the English or a translation model on the Chinese and the English. And we should take as a feature function the log probability of the model. And an example is, for instance, something that occurs in our output is NP, NP, and VP, up NP. Clearly that's wrong. There's an and before the VP. So we would hope that we get this second sequence when we, as more probable. Another thing was tried is a projected part of speech language model. The motivation here is that the baseline system has a weak model of word movement. So the idea is to use Chinese part of speech tag sequences as surrogates for Chinese words to model movement. And the implementation is that the Chinese part of speech sequences are projected to English using the word alignment, and the relative positions are indicated for each Chinese tag. The feature function is simply the log probability of a trigram language model built on the projected Chinese tags and positions. This has some similarities to the HMM alignment model of Stefan Vogel, but it's on the part of speech. And here's an example of what would actually be evaluated here. So you can see that, for instance, the number 14 was translated by translated from the Chinese of a number followed by a measure word. We also tried to alignment templates using part-of-speech features. So in the baseline alignment template system, we only use consecutive words, but this may be too lexically dependent and not generalized. So the idea here is that we use the probabilities of consecutive word phrase alignment templates. We smooth the probabilities of these using part-of-speech tag phrases. And so, for instance, we can work at the level of a sequence of Chinese or English part-of-speech tags and templates, so monolingually. So, for instance, that we have a Chinese, we have an NN in Chinese, or in English, we have a JJNN sequence. We can work with translation pairs, so an alignment template might be to translate a NN to a JJNN, or an NN to a JJNN. Or we can work on lexicalized part-of-speech sequences in pairs. So in the monolingual case, that would be simply adding the word market, and in the bilingual case, we're modeling, translating from NN to JJNN, given that the word is market. Here, unigram language model computes the generative probability, and if we're working with a translation model, we combine this with the conditional probability of a pair given the Chinese part-of-speech sequence or the English part-of-speech sequence. So here are some results. Again, these are on single feature functions tested only on the baseline, and some of these are going to be useful in feature combination, even though they're actually below the baseline here. So we have things, again, this is just a few of the feature functions that were tried in these families. And of course, since this is a shallow syntax, we could try an awful lot of feature functions. We in fact tried 244 that would fall into the shallow syntax category. And these are just some of the, just the ones that I talked about now.
So what's baseline again?
31.6.
And the significance level is what?
So on the single feature function level, these results are probably not significant. So we're going to have a problem later on, which will be addressed in later talks of how to combine all of these feature functions that each have a little bit of information into something that gives us an overall score that is significant. Okay, next, Zen is going to talk about 3 approaches to improving punctuation.
Zen is an undergraduate. Maybe you could say where it's from.
Okay, I'm one of the undergraduates, and I'm from Mount Holyoke College. In case you don't know, it's in Middle Massachusetts. And so a few feature functions that's in the shallow syntax for deal with punctuations. And they have also triggered the start of adding new hypotheses to the embed. We noticed that there are often ungrammatical punctuations, especially on parentheses and quotes, that affect the syntactic quality of our output. We tried 3 different approaches to solve this problem. The first one is to penalize the occurrences of unbalanced parentheses, and the second one is a direct correction of the wrong parentheses in the embed hypotheses. And the third one is to check the alignment of punctuation group English and Chinese words. So the first approach, the feature function that numerically counts the occurrence of these problems in the English sentence. So in the example, you can see that the produced output from the baseline has these annoying parentheses in the middle, and by adding this feature function, we depress this sentence from being the top, and the new output does not have such a problem. Unfortunately, in this case, the translation does not seem to be as good as before. So ideally, we want the parentheses in the correct positions with the better translation, if we compare it to the reference. There lies another problem with this approach. When most of the hypotheses make similar mistakes, this feature function provides less harmful discrimination among them. Therefore, a correction mechanism is desired, which leads to our second approach. Instead of scoring each hypothesis, we can make a few changes by inserting the parentheses into their correct positions and deleting the unaligned ones. That means we're actually making new hypotheses. We're able to do this due to the fact that minor changes in punctuations do not massively affect the existing feature function values, and thus we keep using the old ones. The big changes, however, if you want to use them, are not practical here, since we won't have accurate feature function values anymore, and thus it becomes hard to calculate the MBAT scores. Therefore, adding new hypotheses to the MBAT list is a challenge under this framework. After implementing the correction of parentheses and quotes, we got triple improvement to the baseline score, implying that quote and current soundness does not affect the blue score very much. Here is something more global. I still keep using parentheses as examples here, even though this feature function applies to nearly all punctuation. Both the Chinese and English words are grouped according to their nearest punctuation, and each character here stands for a Chinese token, and the number is its position in the Chinese sentence, while each character here stands for an English token, and the number is the position of its aligned Chinese word in the Chinese sentence. So the feature function calculates the percentage overlap of these groups. It penalizes word movement around punctuations. As we can see, this word gets moved out of the parentheses and is penalized in score. And the penalty is severe if we have missing punctuations, since all the words following that missing parent join the wrong group and affect our score more dramatically. The example is the resulting output within our expectation that this feature function make the parentheses have the desired word enclosure instead of leaving something outside incorrectly. From the human evaluation, we can see that out of 3 different output sentences, 3 sentences from without the feature function perform better, and 7 from with the feature function perform better, and 1 of them are as bad or as good in terms of parentheses and quotes readability. But this improvement is not appreciated by the group, unfortunately. So much for shell syntax. And after the break, we'll have Kenji start talking about the syntax feature functions. Thanks.
The break will last till 10:40.